So in this lecture, we're going to talk about object-oriented concepts. And we're going to focus in on classes and how we can also apply some of the other foundational concepts, or you could say non-object oriented concepts such as functions and variables within the context of object orientation and classes specifically. Okay, we're going to have a look at how we can create constructors, which are special member functions within the context of a class. We'll have a look at how they can be overloaded. So we'll look at the difference between default constructors and non-default constructors. We'll also have a look at how we can instantiate classes. And this is another object-oriented concept. And of course, when we instantiate a class, we create an object. Okay, therefore we can create many objects of a class. We'll also have a look at how the object-oriented principle of encapsulation is outworked within our code, and that's through access modifiers, where we can set up things to be public, private, or protected. Okay, we'll also have a look at another object-oriented principle known as inheritance, where we can set up classes to inherit code from other classes. Okay, we'll also have a look at abstract classes, and we'll also have a look at other aspects regarding the project structure and how we can design our classes through UML diagrams. And so let's start by clarifying the different terms that we're going to use in the context of C++ and object orientation, because these terms will differ depending on which language you look at. Because in C++, functions declared within the context of classes are known as member functions, whereas in other languages, such as C# and Java, they're referred to as methods, where it's not possible to declare methods, in that case, outside of classes. Whereas in C++, we can actually declare functions outside the context of a class above the main, for example, like we did in the first week. Okay, but in C# and Java, we can't do this. Every method that's declared, the equivalent of a function that is, has to be declared within the context of a class, even if it is static. Okay, and there's not going to be an object made of that class to call the method. It's still got to be declared within a class. All right. So we're going to refer to these as functions and member functions specifically when we declare functions within classes. Okay, and then variables are also known as member variables or data members. Okay, I think data members is probably the more common term that you'll see. Okay, so again, variables go by different names depending on which book you read. Sometimes they're referred to as attributes, data, or variables, but they're all referring to the same types of characteristics of a entity. Okay, and we can use them. We can declare them outside of the context of a class, whereas in C# and Java, again, they have to be declared within the scope of a class, regardless of whether they're static or dynamic. Okay, but of course, in C++, we've seen how we can declare variables outside the context of a class, as we saw in the main function. But of course, even though the different languages have a slightly different approach and different terminology, of course, the classes do look similar in terms of they have a name, they have blocks of code which perform tasks. Okay, whether they're called functions or methods, they still do organize code into groups. And then, of course, they have characteristics. So they have some form of attribute or variables to store data for objects of that class. So let's talk about how we would write a class in our code. Okay, so assuming that we've worked out what entity we want to represent as a class, remember that classes are going to be generic. They're going to be the general version, the general template of a entity of which you then make specific objects for. For example, we could have a student class, or in this case, we've got a player class from which we create student objects that are specialized to a particular student or specialized to a particular player. Assuming we've worked that out, about, we then want to actually code it, don't we? So assuming that we've planned all of that and we know exactly what our classes should represent, we can code it by using the keyword class and then followed by the name of the class. Okay, so if we want to represent players, that would be class player. In this case, it's basic player. It's probably referring to a specialized version of a player. Perhaps there are other types of players that are going to be represented by other classes. But that aside, once we've specified the keyword class, you'll see that appear in blue, and then the name of the class, we then have to follow that with a pair of braces, and within those braces is where we're going to declare our data members and our member functions so that they correspond with that class and are part of that class. So all the objects created of the class then have access to those data members and member functions. And a point about style is that you'll note that the opening brace actually appears on the same line as the class declaration. And this is actually Kernighan and Ritchie's style from the original C language back in the 1970s. So if you want to follow that, you can do. I think that's still the de facto style of C++. However, you'll probably see in other languages like C# and Java that the opening brace is actually put on a new line, so it would actually appear underneath the class declaration line and be on a line by itself. Okay, but that's just a minor point about style. The main point really that we understand is what a class is and what it contains. Okay, so you'll see in the blue box here, underneath the declaration, the class declaration, the second line is we declare a data member. It's a standard integer variable called size, and then underneath that we have a member function which does something. Okay, and so just an example of a function that we looked at in the previous week, just declared within the context of a class. All right, and then underneath that, we have the closing brace of the class. And note here that there's actually a semicolon that needs to be included. And this is unique to C++. You won't find this in C# or Java. They don't have semicolons at the end of class declarations. But in C++, we do have a semicolon. Okay, so just remember to include that when you declare your classes and define the contents of them, the data members and the member functions. But here in C++, this does actually give us the option of creating our objects of the class at the end of the class declaration. Even though it says optional variables, those are optional variables of the class, as opposed to the data members, which are the attributes of the class. Okay, so if you know your objects and you have a list of predefined ones ahead of time, and you want to declare them, you can do so at the end of the class declaration, in between that last brace and the ending semicolon. Okay, and the final point to note is that functions defined inside the class are implicitly inline. Okay, you can actually explicitly declare functions to be inline. I think we've got a slide on that later, so we'll cover that then. Okay, but just know for now that functions defined in the class are implicitly inline, implicitly stated. Okay, means it's not stated explicitly, it is implicitly inferred. Okay, so those are just some minor details there. The main point is that we know how to create a class and define the data members and the member functions. Okay, so let's move on and say a little bit more about the difference between declaring and defining member functions within a class. So in the previous slide, you saw that we both declared and defined the member function. It was just an example of doing something within the class, which is perfectly legal, it should be said. But remember, we also said in the previous presentation that we can actually separate the declaration of the function and the definition of the function. Remember, we called this prototyping in the previous presentation, where we declared the function above the main, but then defined it underneath the main. Okay, so just in case we refer to the function within the main, we have to declare it first so that we have something by which we can then look up and find the definition. Okay, so we can do that here as well. When we talk about class scope, we can actually declare the prototype for the function, or we could say the interface within the class, the actual braces, and we can then define the function outside of the class. Okay, the actual declaration of the class. And there's a number of different configurations here. Sometimes you might see the interface of the class with the prototypes of the functions actually in the header file, and then the implementation, the definition of those functions in the CPP file. But optionally, you could also have the definition of the class within the header file, as well as the declaration of the class, the prototypes within the header file as well. So whatever format that you go with, whether it's declared and defined together, or whether they are separate and in separate files, or within the same file, we just have to make sure that we refer to the class and refer to that function being part of the class. And in fact, you'll see that here in this slide, where we've got an example of the hello function, which is both declared and defined within the class declaration. As you'll see there, we've got the function signature as well as the contents of the function, the implementation of the function, which just prints out hello to screen. And that then underneath it, we've got a declaration of the goodbye member function, but we just got the prototype, the interface, if you like. We haven't got the contents of that function. Okay, so we then have to define it elsewhere. Okay, in this case, it's presumably still in the same file, but just outside the scope of the class declaration. So here you'll notice that we have to refer to which scope the function is to be found in. This is where we need to use the scope resolution operator. Okay, so you'll see here that we need to define the return type for the function, first of all, which is void in this case, and then the class name, and then the scope resolution operator, which is the 2 colons, all right, and then followed by the function name. Just in case there's a duplicate function in a different class, we need to define what scope we're referring to, which class this function is residing in, and which one we want to code. Okay, so just remember that syntax when you come to define member functions outside of the class it's declared in. Okay, so I hope that's clear. If in any doubts, just refer back to these slides to check the syntax for how to define and declare functions. But let's move on now and have a look at a special type of function, which is the constructor. And it used to be the case that we couldn't initialize data members within the class declaration itself. Prior to C++ 2011, we weren't able to do this. I think at the time of recording, the latest version is C++ 17, and in that version, it is actually now possible to initialize data members. But back in the day, the constructor used to perform the purpose of being the function where we could initialize data members. And because the constructor is the first function that's called when we create an object of the class, and if you haven't created objects of classes before, we're going to come to that in a few slides. And there you'll see that when we actually create the object of a class, in that line, we actually call the constructor, the function with the same name as the class. Therefore, the constructor was the natural place, and still is the natural place, to initialize the values for the attributes that correspond to that object. So hence why it's known as the constructor, because it helps to construct and initialize the object itself. And so let's have a look at how we would declare and define a constructor for a class. And even though, like we said, in the newer versions of C++, it is possible to initialize data members within the class itself, the constructor can still be a useful and natural place to do this. So this is still good practice and still encouraged to make use of the constructor. Okay, so we mentioned before that it's a function, and it has the same name as the class. So when we define the constructor, we have to use exactly the same name as the class. And that means also the same casing as well. If we use uppercase and lowercase, we have to use exactly the same format of class name there. Okay, but the unique thing about the constructor is that it doesn't return any values. It doesn't have a return type to it. We don't even state the keyword void before the actual constructor name, which is the class name. So in this case, it would actually just be the constructor name and then a pair of parentheses and then the braces where we would place the statements to initialize the data members inside. Okay, and so that would be the basic format for declaring and defining a constructor. And we should say that this is known as the default constructor because it doesn't take any parameters, or at least if we set it up to not take any parameters, it's known as the default constructor. But if we start creating overloaded constructors, so functions with the same name, but take a different parameter list, those are known as non-default constructors. Okay, that's where we can create overloaded versions that take in values, let's say, for the data members that we want to then assign to the attributes of the class for a particular object. And here in this slide, we actually see an example of a non-default constructor, which takes parameters. Okay, we don't actually see the default constructor here. We just see one example of a non-default constructor. But we're going to take a look at how the two can work side by side in just a moment. But just before we do that, let's take a look at this full example here. So if you have a look at the first blue box at the top, you'll see that we are defining the player constructor. Notice it's a function, so it has the same name as the class, capital P player, and then a parameter list. It takes a integer parameter, the player number, and also a string parameter, the player name, which it then assigns the values for those parameters, which are going to be passed into this constructor, to the attributes of the class, so that the object of this class will have those values for those attributes, okay, those data members. All right, and if we have a look at the second blue box, the blue box at the bottom of the slide, we'll see that there's an alternative format for assigning this parameter list. If you have a look at the player constructor here, you'll see that we actually have the same parameter list, but then we have a colon and then assign the player number to number, which is the data member, and then the player name, pname, which is going to be passed to this constructor in the parameter list, we'd actually then assign that to the name attribute, the name data member for the class. Okay, so that's a convenient way of assigning the values of the parameter list to the class attributes, the data members, before we even get to the braces. So you notice there's an empty pair of braces that follow that initialization. So we don't even have to write anything within those braces because we've already done what we wanted to and initialized the data members within that. So that's just an efficient and alternative format for initializing the data members. And we might also see this being used when we get into inheritance, where we can actually pass things directly to the parents constructor before we even get to the braces. Okay, so we'll have a look at that when we get there. Okay, let's move on now. All right, so here we go. We mentioned earlier that we were going to talk about overloading functions, and we can do this in the context of constructors and also other member functions. Okay, it doesn't apply just to constructors, it's applicable to every type of member function. And by overloading a function, it gives us the advantage where we don't have to set up a function of a different name. We can actually keep the same name of function, so that may describe the meaning of what it's trying to do. For example, here in this example, we've got a function called sum, which adds two numbers together. And rather than having a sum of integers function and then a sum of floats function, which have different names, we can actually keep the same name of sum and then just pass in different parameters, different type in this case, and then return the matching type. All right, so that we can apply that some logic or meaning, semantics, what it's actually supposed to be doing as a task to a variety of different types or a different number of parameters that we may want to pass in. And of course, this applies with the constructor as well, where we have two constructors of the same name, both have the name of the class, remember? But we may want to pass in a different parameter list. We may want to pass in specific values for the data members, where we actually assign them in the constructor itself, rather than just initializing them to 0. So coming back to this example here, where we mentioned we've got the two sum functions, which allow us to pass in 2 integers or 2 floats, add them together and then return them. In order to distinguish between which function is called when, we can help the compiler out by explicitly stating what type of data we're passing. Because, of course, the main difference between the two types is that floating point numbers allow us to work with decimal places, but integers are limited to whole numbers. However, we can actually pass decimal place numbers to integer variables, but they may either be rounded up or the actual decimal place is cut off. So therefore, we have to make it clear to the compiler that we want to pass the decimal place values to the function which will accept floats rather than integers. Okay, we don't want to get them mixed up. And so when we come to look at the function calls, the compiler can implicitly work out that we're passing integers in the first call to sum, because we're dealing in whole numbers there. So therefore, it would look up the function that accepts integers, which is the first one we see above. But then with the second call, where we're trying to pass 3.25 and 8.45, by stating f there, short for float, we then are being explicit in saying that we want to pass to the parameter list that accepts floats, not integers. So that then prevents the compiler from accidentally passing them to the parameter list which accepts integers. Okay, the first one again. We tell it explicitly that we want to pass it to the sum which accepts floats. All right, so this is something we have to look out for when passing numbers. It's not a problem when you have a different number of parameters, because the compiler will just match the number of parameters passed to the parameter list which accepts those number of parameters. But in this case, of course, both of those functions accept 2 parameters. So we have to distinguish between them by the data type. Okay, so I hope that made sense. This is the concept of overloading that we can apply, and we'll have a go at this in some of the exercises. But for now, let's keep moving here, and now let's go on and talk about how to instantiate an object. Alright, so when we talk about creating objects of classes, we're essentially creating a variable of class type. You may have heard objects referred to as an instance of a class, and that's exactly what they are, because we can create multiple instantiations of that class type in the form of objects, or variables, if you like. An object is just a fancy variable. Rather than a variable which contains one value at a time, an object can contain multiple attribute values, because remember, you usually define multiple characteristics for a class, so lots of variables which will each hold a single value, as well as functions. So an object just holds multiple data, as opposed to a variable which just holds a single piece of data at a time. And to create a variable, an object of class type, this is going to follow a similar format to creating a variable of a primitive type, such as integers or strings or characters or booleans. Okay, remember, for those standard variables, we need to declare the data type and an identifier name. It's the same with creating objects of classes. We need to define the class type, the type of structure that we want to create a variable of. So here we've got basic player as the class name, and then my basic player as the object name, the identifier. Yeah, I hope you see the similarity between that and, say, int number or string name, where you have the type and then the identifier. And then you'll notice in the second line we've got player, which is class, the class type, and then my player, which is the object name. And technically these are static objects. They're created on the stack as opposed to on the heap, because we're not using the keyword new here, which tells the compiler to allocate memory from the heap, the dynamic data store. We're going to come to creating dynamic objects a bit later. Okay, but we can still call the constructor through a static instantiation of a class. And even though it's not as explicit as the dynamic objects where you actually have a call explicitly to the constructor, the function with the same name as the class, here we've actually put the pair of parentheses after the object name, and that will act as a call to the constructor, the function of the same name as the class for that type. So here in player my player, we're passing in two values, the value 7, presumably the player number, and the name, David Beckham in this case, to the attributes of that player class, and presumably the constructor will assign them to the class attributes, the data members. Okay, so that acts as the call to the constructor. All right, we couldn't actually say my player dot player and then parentheses. We can't explicitly call the constructor outside of the declaration of the object. It's not like another member function which can be called through the dot notation, which we're going to see in just a moment. And the only other thing to say here is in the first line where we say basic player, class name, and then my basic player, the object name, notice we've got a semicolon after that. We haven't got a call to any type of function. And if we're not intending to pass anything to the constructor, i.e. no values to pass and then assign, then we don't even have to include the parentheses there. We can just have a semicolon afterwards. And yes, like we were just saying, we can't call the constructor, we can't invoke it through the dot operator. We wouldn't be able to say the object name dot constructor outside of declaration of the object, but we can call other member functions explicitly. And we do use that syntax of using the dot operator. And this allows us to specify which object we want to call that member function for. Because of course, if you have multiple objects, you may want to call a function for one of the objects, but you may not want to call it for one of the other objects. So it allows you that control and that freedom to call functions for different objects at different times, because of course they're all unique, they're all different. Even though they're made of the same template, they all have access to the same member functions and the same attributes. Of course, they have unique values for each of those data members, those attributes. Okay, so we may want to call functions for each of the different objects to amend and to print and to change those attributes at different times. Okay, so that dot operator is going to be really important to allow us to be specific to each object so that we call the function for that particular object. As we indeed see here, we see my player, which is the object name, dot display name. So it calls display name for that particular player. So it would hopefully display David Beckham. Okay, but for another player, we want to call the display name and then see the name for that particular object. Okay, so that's the advantage there. Right, let's talk about access modifiers now. And remember, this is how C++ and indeed other languages actually implement the concept of encapsulation. Okay, remember, encapsulation is also known as data hiding. So this is where we can define the amount of access that we're going to give to certain parts of the class. There's actually three main types of scope, which are public, private, and protected. So public, as the name implies, means that data members or member functions that are declared as public or declared in the public interface in C++, as we see here, it's actually declaring a public interface followed by the colon, and then underneath that interface is where we would include the declarations for members which would be public. So we actually have to place the declaration of members in these interfaces if we want to have that level of access to them. And of course, you'll see an example of this in the next slide. But as we mentioned, public is where we can declare members to be visible, not only to the class that they're declared in, but every other class that may want to have access to them. but members that are declared within the private interface are only accessible to the class that they're defined in. So if we declare a member to be private, it can only be called if it's a member function, or modified, or even accessed if it's a data member through the class itself. So typically within the member functions, we'd have access to this particular data member. So those two are probably the two we're most familiar with if we've done any level of object-oriented programming before. But protected is where we get into the realms of inheritance, and we're going to come on to that. You'll see that applied, but we might as well tell you about it now so that you're ready for it. And so protected acts like the in-between public and private for an inheritance hierarchy. I like to use the parent and child metaphor because I think it's a good one to relate to as humans. Where you have a parent class and a child class, it means that you can declare members to be private to classes outside of the hierarchy, but they are public to classes within the hierarchy, whether it's the parent or the child. Okay, the parent obviously can see it because it's declared within that class, but the child and the children classes can also have access to it. But other classes outside of that hierarchy, that i.e. are not children, not inheriting from this parent class, cannot have access to it, cannot see it. Okay, so we're going to get into that. We're going to look at inheritance in a bit more detail later on, but that's just a quick summary of the different interfaces that we can declare and specify for our classes in C++. So if we have a look at this example now, you'll see that we've actually declared the data members in the private interface. So after the private colon there, not in the public interface, which is public colon. Okay, that's where the constructor is, which of course has to be public, by the way, for you to actually call it when you create the object, because of course you're likely to be creating objects of this class outside of this class, typically within the main. So it does need to be a public member to actually have access and to be able to call it. And then the display name is also public because we're going to want to call that typically after we create the object. So this is typical OO convention, trying to keep the data members, the actual data, to be private so that it can only be modified within the class. Okay, it's tightly scoped, whereas the actual member functions themselves are public, so that we can access and call them through designated objects created of that class. And the last thing to say is that if you don't define any interfaces, the private, public, or protected interfaces, these data members will be private by default. Okay, so that automatically defaults to private if you don't otherwise specify that it should be public or protected. And the advantage of having an interface in C++ is that we don't have to keep writing the keyword public, which we would have to do for other languages such as Java and C++, where we have to state whether it's public, private, or protected within the actual data member declaration or the member function declaration, or of course in those languages they're called methods. Okay, so it's having an interface where you can define any number of members within them, saves you having to write it out multiple times. Alright, so let's take a slight deviation from object orientation and talk about structures for a moment, or structs as they're otherwise known. And structures were originally created in the C language, so C++ does include them for backwards compatibility with C code, but of course this was before the days of object orientation. Object orientation was a paradigm that was emerging in the 1980s, but in the C language before that, there wasn't such a paradigm available. So the advantages of OO, the principles of encapsulation, inheritance, polymorphism, weren't present back then. So therefore, structs by default are public. And everything to do with the members, the data members and the member functions will be public, which of course this is in contrast to the OO paradigm, which would guide us to use private data members as opposed to public data members. And of course, inheritance, we're going to get on to talk about inheritance. There are actually different ways of doing it. You can actually perform inheritance publicly, privately, or in a protected sense. But of course, with structures, even though inheritance can be applied to them, it's only going to be in the public sense, which actually is the predominant way of performing inheritance. We're going to get on to have a look at that, but you'll find that public inheritance applied to classes is actually the typical way of performing inheritance. But a struct does actually have the same type of internal structure definition of a class. You can define attributes or characteristics of a struct, and you can also define functions in a struct as well. So if these don't need to be private, then this actually can be a good alternative to a class. And then rather than creating objects as we know them in OO terminology of classes, we just create variables of structs. And actually, if you remember back to the first presentation when we had a structure for the time, that's an example of that. That's where you can just define a variable of the certain time structure to get access to the different attributes like minutes, seconds, hours, days, months, etc., etc. Okay, so let's move on now and get back to talking about OO, and we're going to talk about the difference between static objects and dynamic objects. So let's contrast the creation of the static object with the creation of the dynamic object. We've already seen that to create a static object, that is a variable of a class on the stack, hence why it's static, we have to write the class name, which acts like the data type for the variable. If you remember, like we would write int number or string name, we have to write the class data type and then the identifier, the name, which is the object name in this sense. Okay, so an example of that would be here, where we write player as the class name, and then my player is the object name. And then remember, if we're not going to be passing any parameters to the constructor, the function with the same name as the class, we can actually leave out the parentheses after the object name and just write the semicolon. However, if we do want to pass parameters, we'd have to include the parentheses and of course the values inside them, as we saw previously. And after we've declared the object, we can then call member functions by using the dot operator. Okay, like we see here, if we want to call the print function for this player object, my player, we would write myPlayer dot print, and then as it's a function, obviously write the parentheses and the semicolon. All right, so that's the static object which we've seen. If we contrast this now with the creation of a dynamic object, we see that we've got a different syntax here. So first, we'd actually create a pointer of the class type. As we see here, remember the asterisk is the pointer. So we would say class name, player in this case, and then asterisk, pointer, my player. And we don't need to have the parentheses here either, so we can just say semicolon. So we actually create a pointer which will point towards an object memory address which is to be set up on the heap, okay, different to the stack, all right? And the way we can distinguish between the two is that we can use the keyword new, okay? If you pay attention to the second blue box in the middle, you'll see here that once we've set up the myPlayer pointer, you can do it in the same line or a different line, you can say my player is going to be assigned keyword new and then an explicit call to the constructor, because notice there it's a function, we see the parentheses, and then notice it's got the same name as the class, player. Cast your eye up to the class name again, player as well. So a function of the same name as the class is the constructor. All right, and even if we're not going to be passing any values, any parameters, we would still have to have the parentheses, the brackets, after the constructor call, because we're going to be calling it as a function. Okay, so that would assign a object memory address on the heap, so we need to point towards it to get access to it. It's not declared on the stack, we don't have convenient access to it, so therefore we have to create a pointer so that we can refer to this object memory address on the heap. And then rather than using the dot operator to be able to access member functions for that dynamic object, we actually have to use the dereference operator, or colloquially known as the arrow, because it looks like an arrow. You can see there it's the hyphen and then greater than symbol, the chevron, pointing to print. Okay, so think of it like an arrow. It points to the print function in exactly the same way. It just replaces the dot operator. So we still have to specify what object we want to call the print member function on, and we do that here by just saying my player point towards print. All right, so that's the difference between static and dynamic. The heap is obviously a larger data store, so it's convenient for larger objects and storing arrays as well, which have lots and lots of elements. Because the stack has a limited size, we're going to see that in a few weeks when we talk about stacks. Stack therefore is used for smaller pieces of data, temporary variables and function pointers. And here we see an example of both a declaration of a static object and a dynamic object. If we have a look at the main function here, we see that we're first of all creating a static object, which is conveniently called myStaticObj, then calling the print method on that using the dot operator. And the print method, of course, resides in the class called myClass. So that's where that resides. It's in the public interface as well, so we can access it. And then if we go back to the main, underneath the call to the print of the static object, we create a dynamic object, which, remember, as we said, we have to create a pointer, first of all. So here we go. It's myClass and then asterisk myDynamicObj. And then underneath that, we assign that pointer the address of a object created on the heap, and of course to create the object we call the constructor. So notice the parentheses indicating it's a function, and myClass of course is the name of the class, so a function with the same name as the class is the constructor. We don't actually have a constructor defined here, but that's not a problem because the compiler will just automatically create one at runtime, even if it doesn't do anything. It still invokes that to create the object and create the memory address, and of course that's the keyword new. And then once that's set up and we've got the pointer set up to point to that memory address, we can then dereference or point towards, using the arrow, the print function for that class, for the class type. So for that object, we refer to the print definition, which is in myClass, of course. So there we go. That's a contrast between the static and the dynamic creation of objects. And let's talk about passing objects as pointers now. So if you remember back to the previous presentation on functions, where we had a look at the different methods for passing data by value, by reference, by pointer, and by constant reference, when we had a look at passing by pointer, we only passed in primitive pointers to primitive type values like integers or strings or characters. But now, because we're creating dynamic objects and creating pointers towards them, we can actually pass those pointers to functions, and that might allow us to do something with that object within the function. So if we have a look at this then, notice here in the first blue box on this slide, we've got an example of a function display which in the parentheses creates a pointer p, notice the asterisk there, of player type. And because player is the class, we're expecting a memory address of that class type, or i.e. a memory address which stores something of that class type there at that memory address. That means when we come to call display in the second blue box, notice the first line of that blue box there is where we instantiate the dynamic objects. Notice that syntax again. Create the pointer called myPlayer. It's of player type class, that is, and then call the keyword new, which creates a new object on the heap, of course calling the constructor as well, which means that we have myPlayer, which is a pointer to an object on the heap, which is of player type, so that we can actually pass myPlayer, which is the pointer, points to a memory address, to the receiving pointer. Okay, so that P in the display function can then dereference a attribute, if it's public, that is, which I presume it is in this case, as it's dereferencing it, okay, to actually print it to screen. So this is another convenient way that we can use our dynamic objects and our pointers towards them in able to reuse our functions for any different object that we wish to print or display or add or do something with it. And this technique is also applied to creating anonymous objects. If we have a look at the blue box here, we see that first of all we're creating a class called weapon. And then in the load function of this class in the public interface, we are setting up a pointer called newMag, which is of type magazine. Okay, another class presumably, which we're expecting when we call load. All right, so this will receive a pointer of type magazine. It points to something of magazine type, basically. So that when we come down to the main, notice that we're creating a dynamic object of weapon. It's called mygun. We've got that syntax again, okay, but we're not actually going to create a named object or pointer for a magazine object. Notice instead that in the next line, when we call the load function of the mygun dynamic object, within the parentheses, we've actually got that syntax again, the second half of the object creation syntax. And remember that the keyword new tells the compiler to allocate memory on the heap for an object, so that we're creating an object on the heap of magazine type. We just haven't got the first half of that typical statement, which is where we declare the object name, or the pointer, if you like, the pointer name that we refer to. So therefore, because we haven't got that, we've got an unnamed object, which is what we refer to as an anonymous object, an object without a name. But because the keyword new creates the object on the heap, that is a memory address that we can then pass in to the pointer that's to be received in the load function to then assign a new magazine to that. It's actually a local dynamic object of the weapon class itself. Basically, this is useful because it saves us having to write out all the different names for the objects. If we don't need to name them, then we can save time by not naming them. Okay, so we're going to have a go at this in some of the exercises throughout this module, so you get to apply this. All right. Okay, so we've now arrived at the inheritance section of the presentation. We've been hinting at inheritance for some slides now, so now that we've arrived at the section, we can spend a few minutes discussing it in a bit more detail, and it's going to be a very important principle to learn how to use, because it's a key object-oriented principle, and if we apply it correctly, it's going to make our code much more efficient. All right, so it's definitely worth getting the hang of. All right, so when we create our classes, it's likely that we're going to want to create unique classes for different entities. Like what we did earlier with basic player, that's a type of player, but we may want to create a basic player class which has attributes that are going to be unique to a basic player and may not be shared with an advanced player or a different type of player that in turn may have unique data members and member functions as well. It's likely that we're going to want to create unique classes for our different entities. However, those classes may well share attributes, data members, or member functions as well. So rather than having to duplicate the same data members and member functions across all the related classes, what we can do is we can actually group them together, those common data members and member functions, into one class. And typically this is going to be what we refer to as a general class, or a generalized version of a class. For example, a player, which will hold all of the common attributes and functionality of all the players. And that then allows the specific types to then draw from that common, if you like, pool of shared functionality and data members. All right. So this is what we refer to as inheritance, where we can set up a general class that the specialized classes, like the different types of player, can inherit from the general class. Okay, so that's the underlying concept. And here we've got some different examples, such as a dog is a type of animal, as is a cat. So they both have 4 legs, and therefore we could have an attribute called number of legs, which could be in the animal class, and then inherited by dog, cat, and other animals. And next, we've also got a general building class, which has lots of shared attributes and functionality by different types of buildings, such as a house or a office or a stadium. So lots of them will have seats, lots of them will have rooms. So therefore we can delegate those common attributes or data members, if you prefer, to the general class of building. Okay, so I hope this is helping to convey the concept of inheritance. I appreciate it's quite an abstract concept and hard to get a handle on. But what I find helps me is thinking about the relationships between the general class and the specialized class in terms of the equivalent parent class and child class terms. Okay, the parent class refers to the general class, which has the common pool of data members and member functions, and then the child class inherits from the parent and then specializes that with their own data members and member functions. Okay, so I find this is quite a helpful metaphor because, of course, as human beings, we are all children of our parents, and therefore we all inherited our parents' DNA and genes and other types of attributes that they have. And of course, we also inherit estate and wealth from our parents when they pass on. Okay, so I find this is quite a relatable term to refer to this inheritance relationship. So just think of that if you're not sure which of the classes is the parent and which one is the child. The parent has the common attributes which are then inherited by the children classes. And you may also see these referred to by different terms as well. In some books, you may see them referred to as the base class and then the derived classes, which derive from the base class. Or indeed, you may see the equivalent terms of a superclass and the subclass. Okay, the sub being subordinate to the superclass, therefore inheriting from the superclass. Okay, so whatever terms you prefer to use, I quite like the parent and child terminology. As we mentioned before, that's something we can all relate to. So that's the terms I like to stick with. But just before we move on and have a look at the code, one thing I need to mention here is the basic principle by which we actually implement inheritance into our code. And that is through the colon. Okay, it's a nice simple operator. At the class definition, we just write the child class and then colon parent class, indicating that we want to inherit data members and member functions from the parent. And let's have a look at an example now of using this in the code. And so here on the left-hand side, we have the parent class, which is model, and it has a single member function called draw. And then on the right-hand side, the right box, we have a child class called car. In the declaration of the class, we've stated class car colon public and then model, which is the parent. Okay, so that colon is present, as we just said in the previous slide, to indicate inheritance. And then, of course, we have to indicate what class we're going to inherit from, which in this case is model, the parent class. And the reason why we state public before the parent class is that we have options to inherit publicly, privately or in a protected way. And most of the time it's going to be public because we want to ensure that public member functions, as draw is in the public interface of the model class, we want to ensure that that remains public when it's inherited and accessed by the child, whereas if we stated it to be private inheritance, then all the member functions in the public interface would be private, okay, meaning we can't access them, so no good, okay? So we need to make sure it's public to be able to access them from the child class. And so if we have a look at this slide here, we'll see that we've got an example of a main function where we've instantiated objects of both the parent and the child class, model being the parent, remember, and car being the child. And so we can call the draw function through the model object because that's the parent that has access to that public function. But we can also call draw through the child object as well, because that, of course, inherits the access to that function, in addition to also being able to call the change gear function, which is unique to the child. We wouldn't be able to call this through the parent because it's a one-way inheritance. The parent doesn't inherit from the child, it's the child that inherits from the parent. So therefore the parent doesn't have access to the change gear function, but the child can because it's got public access to the parent, okay, in addition to the functions which are unique and special to that child class. Okay, so thus far we've considered inheritance from one parent class, but there is also such a thing as multiple inheritance, which models the inheritance from more than one parent class. That could be two or even more parent classes, which we want the child classes to gain access to their data members and their member functions, okay? But interestingly, this is a contentious issue because both C# and Java don't natively allow multiple inheritance. They actually restrict inheritance to just one parent class. C# and Java have workarounds where they use interfaces, but C++ actually supports multiple inheritance natively. That being said, though, that doesn't necessarily mean that multiple inheritance is a good thing. Okay, because there are actually a number of negatives associated with this, such as naming conflicts, where parent classes share the same names for attributes, things like ID, name, age, address, other types of attributes that may be shared amongst all the different parents, therefore introducing duplication into the children, and also conflict as well, because which ID or name, attribute or display function or print function should the child call? Should it call it from parent 1, parent 2, parent 3, parent 4, etc., etc.? So therefore, this becomes a difficult issue to resolve if you have those attributes duplicated across your parents. And thus another problem is the diamond problem, where those parent classes also inherit from another class, meaning that a child class at the bottom of the hierarchy draws from two parents, but those parent classes also draw from another parent, or multiple parents perhaps, therefore introducing a lot more duplication of common data members as well as member functions. All right, so just because multiple inheritance is allowed in C++, it's not always a good idea to use it. And the advice from different authors and programmers out there is actually to avoid multiple inheritance because of those aforementioned reasons. And here's an example of multiple inheritance, which has been coded in C++. If we start from the child class, we'll notice that, which is amphibian in this case, we notice that it states class amphibian and then colon, like normal. So it's the same for multiple inheritance as it is for single inheritance. That's where we then state public and then parent 1, which is boat, and then comma, public parent 2, which is car. Okay, so we have to indicate public in both circumstances, as well as the class name of the parent, which we want to inherit from. But if we have a look at the constructor of amphibian, the child class, we notice that we also copy the ID, which is passed into the amphibian constructor, into both the ID, which is in the car class, and also the boat class. So therefore, we've got multiple IDs, okay? We've actually got two. All right, even though the amphibian doesn't have one of its own, it will inherit the access to both IDs. So therefore, at best, that's duplication, and at worst, that could lead to conflicts down the line if we've updated one of the IDs, but we haven't updated the other ID. And also, if you have a look at the parents now, the car and the boat class, you'll notice that as well as both having an ID, they also have the same member function called display. Okay, so again, which one is called when we want to call a display function? And here, if we go back to the main function, we'll see that we can actually specify which of the two display functions that we want to call. But of course, this is extra work because we have to name the class. And of course, this may vary across the parents. We may update the display of one of the parents, but not update the display of one of the other parents. Or we may make changes, or they may not have access to certain attributes. So this would introduce unnecessary complexity into our programs, which is not good. We want to avoid that ideally. So therefore, make sure you think wisely about whether you need to use multiple inheritance or not. Okay, can you design the classes in such a way so that you don't need to use multiple inheritance? So therefore, you can avoid all those potential duplication and conflicts problems. And indeed, much of the advice states that if you can use single inheritance, that's going to save you all of the problems from multiple inheritance, as well as, of course, keeping the benefits of single inheritance. So therefore, that's what we'd advise you to try and avoid multiple inheritance if you can, and instead prefer single inheritance or inheritance from one parent. So now that we've covered the object-oriented principle of inheritance, let's talk a bit more about another object-oriented principle, which is encapsulation. And we've already had a look at this in terms of the interfaces of a class definition, such as the public interface, the private interface, and the protected interface, which are otherwise known as the access modifiers. And these, of course, help to enforce the access to the interfaces of a class. They help to control which class has access to these different interfaces. Members that are public are, of course, widely available to any class, whereas private members are only accessible to the class that they're defined in, and protected members are, of course, only available within the inheritance hierarchy. They're private to classes outside of the hierarchy, but they are essentially public to children classes within the hierarchy. And taking this further and coming back to the heart of object orientation, because data members are directly influencing the object state, the values that we give for these characteristics of an object, of course, define them. So guidelines would advise us to restrict access to the object state, which are the data members, and not allow other classes to have direct access to them, to reduce coupling and also to protect the object state. And therefore, the guidelines advise people who use object orientation to therefore make the member functions, the behavior of an object, publicly accessible, to allow changes to the object state through the member functions. And thus, member functions can be divided into two categories. The member functions that allow you to change the object state, i.e. to actually change some of the values of the data members within an object, are known as mutator functions. Or in other words, you may actually see them referred to as setter functions. That's their more casual name. And on the other hand, we have accessor functions, which allow access to the object state, but don't allow you to make changes. So you just return the values of a particular data member or attribute within the object. And these are more casually known as getter functions. So depending on which book you read, if you see mutators, these are also equivalent to setter functions. And likewise, if you read accessors, these are the equivalent of getter functions. Okay, and just before we move on, there's one last thing to mention, and that's if you want to accidentally prevent making changes in your accessor functions, you can append the keyword const in the function signature to ensure that you return the value of the attribute rather than accidentally modifying it. Okay, and in this slide here, we've got an example of setter and getter functions. So if we have a look at the blue box here, we'll notice that in this class called marker, we've got a passMark attribute in the private interface. So that's following object-oriented guidelines. But in the public interface, we have a setter function which sets the mark, i.e. allows changes to the mark. So notice in the parentheses of this function, we pass in an integer value, which is pmark, which is the value we're going to set for the passMark. And if the passMark is greater than 0, that's then when we assign the pmark to the passMark. Okay, so that is an example of changing the value because we're doing an assignment. We're going to set the value, providing it's greater than 0. That's an example of setting, and an example of mutating the object state. We're changing it in some way, changing a value of a data member. And then underneath that, we've got an example of a getter function, or in other words, the accessor. And notice we've got the keyword const as well, so we're not allowing changes to the data member that we want to return. And we do just that. We just return the value of the attribute passMark. So whatever it currently is at the time of being called, that's what's going to be returned. Notice we've got the int return type in the function declaration, and that will just return it to the place where this function is called. Okay, so it's this type of pattern that we'll see, even if they're not explicitly declared to be setters or getters in the name, functions will almost certainly follow that pattern of functions which will change or set or mutate the object, and functions that will display or return or get the object's state. Let's talk about abstract classes and abstract member functions now. And in other languages, such as C# and Java, there is a keyword abstract that we can use to explicitly state whether a class is abstract and also has abstract member functions. Of course, they're known as methods in those languages. However, in C++, there isn't a keyword abstract defined. So therefore, we indicate that implicitly by the following. We first of all have to declare it to be virtual, and this is a keyword that indicates that the child class is expecting to override this particular method. It should be said that you can actually define contents for a virtual non-abstract member function. So it is possible, if you don't want this particular member function to be abstract, you can declare it to be a normal virtual function, which has a definition of its own and can be called through a parent object, and then that can also be overridden by a function of the same name in child classes. However, what makes this abstract is that we actually assign 0 to this function declaration. You'll see here at the end of that statement, virtual void function name is move equals 0. And that means that this is now implicitly interpreted to be abstract. And because of that, we can't actually create an object of this class or then call the methods, because technically it doesn't have a implementation. We've assigned 0, indicating that the implementation doesn't exist. It's purely abstract, purely a concept. It doesn't have a definition to it. Okay, so therefore we have to provide the definition in the overridden functions in the child classes, which override the abstract functions of the parent classes. And also, because this function is abstract, the class is therefore treated as abstract as well, meaning that we can't actually create objects of abstract classes. We actually have to create objects of the children class, which then define functions with the same name as these abstract functions that will override them. And of course, remember the difference between overloading and overriding. Overloading is where you have functions of the same name but have a different parameter list, whether that's a different number of parameters or different types of parameters, as we saw previously. But overriding is where you have functions of the same name and functions of the same parameter list. So they're identical, but they exist in different classes. Of course, the parent and the child classes. So that the child, in this case, because we've declared the parent's abstract function to be virtual, we're expecting that the child will then override the parent's member function. Here we see an example of this where we have the class iPrintable, which is the parent, and it also is an abstract class because we see here we've got an abstract function. The assignment of 0 to the print function, also with virtual, is a giveaway there. So remember, even though this is not declared to be explicitly abstract, implicitly, because we're assigning 0, we treat it as abstract. Therefore, we can't create an object of this class, of the parent class. Therefore, we have to create objects of the child class, which inherits from the parent class. As you'll see on the right-hand side, the class game object inherits from iPrintable, which we see there with the colon, public iPrintable after the class declaration. Okay, and it too has a print function, which is of the same name and same signature as the abstract version in the parent iPrintable. So therefore, in the main, what we can do is we can create a object of the child, as you see here. It's a dynamic object, game object, pointer obj1, which points to a memory address of the game object, and then call getID, which would actually perform the same thing as the print because we're actually passing that to the cout. But anyway, here in the second example of dynamic objects, we've got something interesting here because we're creating a pointer to a parent object, iPrintable, the abstract class, and then we're assigning an address of a child class, the game object. If this function wasn't abstract, that would then call the print function of the parent, but because it's declared virtual and is also abstract, it's then overridden. The compiler is then actually diverted to the child's print version, which is in game object. Therefore, that should then print that to screen. And this is an interesting concept, actually, because we'll see this being applied in another sense, in a non-abstract sense, like we hinted before, where we can actually create pointers to parent types, which have, non-abstract functions in them. They're not abstract classes, which have definitions for these virtual functions. But then if we assign a child object to that pointer, we can then call the child versions of those particular functions because we've set up the parent to be virtual. Okay, we'll explore this more in the polymorphism section. All right, but for now, hope that just illustrates an example of how to create abstract classes and implicitly abstract functions. Okay, so we've spent some time talking about different object-oriented principles, such as inheritance, encapsulation, abstract classes, and abstract member functions. And to finish off this presentation, we're actually going to be going back to where we started in talking about classes and how to declare our classes and how to define them. And in C++, we have the option of actually separating the declaration and the definition parts of the class, where we can place the class's interface into a H file known as the header file, and then place the implementation, the definition for those member functions into a CPP file, a separate file that then has an include statement to link the two files together so that when the compiler sees a reference to a member function, it can then look up the implementation of that member function and go to the designated place where that's implemented. So in Visual Studio, we can actually do this quite easily by using the add class feature. And we're going to have a look at this when we get into some practical examples where we can actually create the class name, and that also creates the header file for that class as well as the CPP for that class. And this can be quite useful actually in separating the header file and the CPP file, because often the developer's only going to be interested in the high level view of the class, the interface which describes what the class does. And hopefully if the member functions are named appropriately, then the developer will be able to tell exactly what the function is going to do just by the name of the member function. As if it's supposed to be displaying information to the screen and it's called display, then they don't necessarily need to see the formatting of that display function in order to know that it's going to display data to the screen. Obviously, if they want to take a deeper look and are concerned about the detail of how the function's implemented, then they may want to look up that function and look at the implementation in the CPP file, but at least the header is a more readable version of the class, as it's the headline summary. It's just the interface, the function names, and the data members, of course. All right, and if we have a look at this slide here, we'll see that on the left-hand side, we've got the header file, as you can see from the top comments, which is date.h, okay? And then on the right-hand side, we've got the date.cpp. Which also has the include statement to the header file version, just so that we can link up the two files so that the interface and the prototypes for the member functions can then correspond to the implementation, which is specified. If we have a look at the header file, we'll see that in the private interface of the class, we've got integer variables being declared. And in the public interface, we have a series of getter and setter functions, and also the date constructor. And you notice that the getter functions actually have the implementation written in them. You notice the braces there, and also the return statement there. So it may also be convenient if there's only one line within the function to actually write it within the header, so that we don't then have to duplicate that in the CPP file for not much gain. If you were to have a look at the CPP, we'll notice that we have got implementations for the set date, which has three statements in there. It sets the three values for the date, day, month, and year. And also the date constructor, as you'll see there, it actually calls the set date. Okay, so it conveniently reuses the functionality of the set date there. Okay, rather than duplicating that. So there are efficiencies that can be made within the CPP if you have that functionality already. And just remember in the CPP to define what scope the function belongs to. Okay, so this still applies, even though we've linked the two classes. We do have to specify what class we're expecting the function to reside in, which of course here is date. So in the constructor, we don't need the return type. We would just write date and then scope resolution operator, the two colons, and then the name of the function, which is date, the constructor. But then for non-constructor functions, such as set date, we'd say the return type before that. So notice here we've got void. Okay, so it's void, and then class scope, and then the scope resolution operator, and then the function name. So that's just an example there of the header file and the CPP file. Of course, when it comes to the main, we have to include the date.h, which in turn then links to the CPP. And this allows us to create objects as we would normally. Okay, so even though we're going to be verging outside of the main CPP, which is where we've worked in for the past 2 weeks, all the other object-oriented principles do apply. And finally, to finish the presentation, just a note on UML, in that UML stands for Unified Modeling Language, and it consists of a series of diagrams. We're going to be referring to the class diagram in this module, and class diagrams are a convenient way of writing down the name of the class, as well as the attributes of the class, the data members, specifying the scope and any parameters, and also the member functions as well in a separate category. So you'll see 3 boxes, one for the name of the class at the top, second one refers to the data members, and then the third one is the member functions. Okay, and it is possible to create these diagrams in a variety of packages. Visual Paradigm, at the time of recording this presentation, is one of the industry leaders. However, Visual Studio does have a built-in package for this, so that's a convenient way of actually creating class diagrams from the code that you write. So it saves you having to write it out separately. If we can automatically generate it through Visual Studio, that's going to save us time. So, and likewise, if you make updates as well, that means they'll be updated automatically. Okay, so within the exercises, you'll start to see different UML diagrams that specify the design for classes, so make sure you follow those as you see them. And here on this slide we see an example of one. As we mentioned, the 3 sections there are the class name, the data members, and then the member functions. And the only thing to mention here, I think, is the actual symbols, which the padlock refers to private, the key referring to the data member 3, the character, refers to protected, so that's the inheritance access modifier. And then lastly, the data member below that with no padlock or key refers to public. And you'll also notice these being applied to the member functions as well. If you have a look in the final section, you'll see the padlock and the key, as well as no icon as well, referring to private, protected, and public. Okay, so that's just a simple key to guide your use of interfaces and the access modifiers that you use. Okay, so this type of diagram can help you design your classes. In fact, it does act a little bit like the interface, so it would mimic like what we'd expect to see in the header file. It doesn't have the implementation here for the member functions, but this should guide our writing of the header files, from which then we can, of course, implement the member functions. Okay, so that brings us to the end of the presentation. That's a lot of content there, so let's have a go at processing all this information and applying it to some of the exercises from this week. And in the first exercise, we are given the UML diagram for the person class, this class that we're going to have to create. Okay, so notice it's got the class name at the top, and then we're also given the member functions. But interestingly, notice we've not been given any data members. Perhaps we have to add them in later. But regardless, for now, we can get started with just creating this class to have member functions. Okay, and there's a number of different ways we can create classes in Visual Studio. If you go to the Project menu tab, you'll notice that we've got an Add Class option, also got a Class Wizard option, and we've also got an Add New Item option, which can also add the header files and the CPP files. And this can also be done in the Class Wizard as well. So lots of different options, but maybe just to keep things simple for now, let's go with Add Class. And if we write person with a capital P, notice that that will automatically create the header file, the person.h, as well as the implementation file, person.cpp. Okay, so this can be done in the Class Wizard as well, but we can do it here just fine. All right, and notice here that also got an option to specify a base class. Remember, the base class is the equivalent of the parent. We don't need to do that for this exercise. That's going to come in the next exercise. So we can leave this blank for now. And let's just press OK here. And that should create the header file, person.h, and the person.cpp, the implementation file. Okay, so there we go. We've got the header file here. And we've got the class declaration with the semicolon at the end. That's important to have. And that's going to be located in the header files folder. Notice there, person.h within there. And underneath, there's a source files folder, which will contain person.cpp, the matching CPP file. as well as also it contains the main CPP, or whatever you named your solution. They usually have the corresponding names. So as I named mine after the module title and the week number and topic number, that's what my main CPP is. But of course, if you chose a different name, it would be under that. Okay, so now that we've got these set up, I think I'm going to pin them just so we don't lose them. Let's keep that there. There we go. So let's have a go now at creating the interface for the class. And as we mentioned, we've been given the member functions here. And the first one is, it's a strange one because it's got a tilde, the squiggly line in front of it. But notice as it's got the same name as the class, it's actually the opposite of the constructor. It's the destructor. Okay, we've got the constructor down below. You notice there, again, the function with the same name as the class, but the tilde indicates it's the destructor. Okay, we'll actually come to this in a future presentation, so we'll ignore this for now. We'll come back to that a bit later. Really, what we want to focus on is adding the member functions that will indicate the state of the entity. Because I think you'll notice here that the member functions here are just describing the movements of the person objects. Okay, it just prints to screen whether it's standing, walking, crawling, or running. All right, so those are the ones we really need to focus on. I don't think we're even defined any functionality for the constructor either, because we have no attributes to define at this stage. So we can actually get away without defining that too. All right, so let's focus on defining the interfaces for the 4 main kind of state declarations. All right, what the person object is doing. So let's start by creating the public interface. Okay, this is going to be important. If we don't do this, by default they'll be private, meaning that we can't access them from outside of the class, this class person. So remember the access modifiers here, because we're going to want to call them from the main file, the main CPP. We do need to make them public, so they're accessible and can be called outside of the proximity of this class. All right, so that's why we need to define them in the public interface. So let's do that. We've been given the return types here, void, and let's write crawl here. And we could actually write the braces and define what we want this function to do. And I think as it's only a single line, it's only going to print out to screen whether it's its state. So we could actually get away with doing it here. We could write this and also need to include all the relevant stream files, IOStream, to get access to that, and space std as well, so that I can call cout and end out, but I have to prefix them with std. I could, my point is that I could actually write that in here. We saw an example of this in the presentation, but maybe just to get used to writing them in the implementation file, just so we get used to the format, probably what I'd encourage you to do is actually define the implementation here. Okay, and just to remind you how to do that, remember that you need to define all the necessary details to match the prototype, which here is the return type, first of all, void, and then you need to specify the scope, the location of the function, which is the person class, and then the scope resolution operator, the 2 colons, and then you'll notice there is the crawl function in the IntelliSense, and that's exactly what we want to define. So if we put the braces after there, as well as parameters as well, let's copy this now from there into here. Okay, and if we're going to do that, we also need to remove the braces from here, because it might get confused that and think that we want to define the functionality here when in fact we want to implement it in here. So we need to make sure we've got braces only in one of the two files so that the compiler knows which one to go to. Okay, so if you're going to follow this format, which I encourage you to do so, make sure for your prototype you just write the parentheses and then the semicolon. And then in the implementation, have all the matching details with the scope, the class name, and the scope resolution operator, and then have your braces with the functionality within there. Okay, and because you're including a link to the header file, you've got the appropriate link between the two. Okay, so when the compiler looks for the crawl prototype, it finds it in the header and then links it to the implementation in here. Okay, that's all set up for us, which is handy. Okay, so with that format, with that template, go ahead and add the rest in. I'll just add the prototypes just in case we need them, but I'm sure you'll be able to add in the implementation as you've just seen it modeled. Okay, as it's in here. All right, and if you do need to add the constructor, remember that doesn't have a return type. That would just be the name of the class followed by semicolon. Okay, you don't actually need to define this because remember that the compiler will create a constructor at runtime if you don't, but if you are going to set up your own, what you would need to do is you would need to define something to go within it, even if it's empty, okay? Because otherwise it gets a bit confused if it can't find the definition for it. So we would have to match that in here. Okay, and just to show you the format for that, that would be the person class name. This is your scope, and then the person constructor. Okay, again followed by a pair of braces, and we don't actually have any data members to define, so we don't have anything to do in it. But we would be expected to add this empty definition if we're going to add a prototype in here. Okay, so there's two options. Either just don't do any of this, or if you are going to set one up for later, make sure you follow the prototype with the appropriate empty definition. Okay, just so it's ready. Okay, and make sure it's in the public interface as well, just so that it can be called when you come to create a dynamic instance of this, or even a static instance of the class, which I think is the next thing to do. So that leads us nicely onto that. I'll leave you to fill in the rest for the run, stand and walk. Won't spend time doing that, but of course that follows the same format here. So just duplicate this and change the details of the function name and what it prints to screen. But now let's have a go at instantiating this class within the main. So let's get that set up here. And we're going to need to include a reference to the person header. We don't have to include a reference to the CPP because remember that CPP is linked to the header. And I don't think we also need to include a reference to the namespace either. Let's just give this a try, because that is also linked in the person.h. Notice that's going to be included there. Hopefully, when we come to run this, we shouldn't actually need to write that because we've got a link to it here. But for any reason, if you do remove the link to person.h later, you would, if you haven't got it linked in any other classes, you'd need to define that within your main CPP. Okay, so just cuts down the amount of code that we have to write. Let's repurpose this hello world statement just to give us a title for this week. You don't have to do this. This is just for my formatting. But if you would find it helpful, of course, you can do it. Just so I know what exercise we're on. Let's add in that. Okay, so let's now focus on creating a dynamic instance of the person class. Okay, and remember for the dynamic instances, we have to create a pointer to an object created on the heap. So how that's worked out is we would first of all set up a pointer of type class that we want to point towards. So as that's going to be an object of the person class, we need to then create a pointer of person type. Oh, did I miss a... Oh no, I think that's for this line, isn't it? So let's now finish this off by then saying equals new. That keyword new is going to instruct the compiler to create the object on the heap rather than the stack. So that's the difference between a static object created on the stack and a dynamic object created on the heap. And then we call the constructor. Okay, it creates it on the heap, and then our pointer points towards that object created on the heap. And we've got an explicit call to the constructor here, which we can leave completely undefined. The compiler creates one at runtime. It's not going to do anything, but that would satisfy that. Or in our current scenario, we have just defined it empty as well. Perhaps it'll be useful later. Okay. Right, so that should be set up, hopefully. And now we can then point towards the member function that we've got defined at the moment, which is crawl. So let's use the dereference operator, the arrow, and point towards it. Okay, and let's give this a run just to check that it runs okay. So hopefully we should see crawling on the screen. Let's just check that we do. And yet we do. That's good. That's good news. So we know that we've linked everything correctly. We link through to the implementation here. All right. So that's pretty much what we're going to need for the first exercise. Hopefully you'll be able to fill in the rest for run, stand and walk, just to get that set up. And just to finish off here, I think I'll get you started on exercise 2, which is about inheritance. So this is where we want to add a derived class, or if you want a child class, which inherits publicly from the class we just set up, the person class. So it gains access to these member functions, crawl, stand, walk, and run. And then the child class also adds in its own member function here, which is fire weapon. It's unique to the soldier entity. Okay, so we can use the same process that we did before for adding the soldier class. We can go to the add class option in the menu. And if we type in soldier, here, notice again, we get the header file, soldier.h, and the CPP file, soldier.cpp. It's good. And here we can also specify the class that we want to inherit from, the base class, or otherwise known as the parent class, which is person. Okay. And that will also link you through to the appropriate person.h file there. Okay, so if we press OK here, we should see this set up for us. Okay, yeah, and there we go. We've got the link there to person.h, and we've got the inheritance already set up for us. It's actually put it on a separate line, which is fine, but that's also sometimes how you see it written there as well. So the main thing is that we've got the colon, we're inheriting publicly, and we've stated which class we're going to inherit from. Okay, so that's good. That's set up for us, which is excellent. And here, I think, again, we've got a similar format in that we want to set up a member function which just prints out that it's firing a weapon. So let's just do this so that we get extra practice. So here's the interface. Oh, and I also need to make sure this is in the public interface as well, so I can call it. So I was almost caught out there because we've got the public inheritance, but we also need to state that this is going to be the public interface. Okay, so please don't get caught out there. All right, so that's that. And then if we go to the soldier.cpp, let's do the same thing again, where we say the return type, and then the scope. So this is going to be soldier, scope resolution operator. And notice we've also got access to the parent class's member functions here, crawl, person, run, stand and walk. So we could actually override them if we want to, but here let's just focus on fire weapon. We just want to implement that. And I think because we've included a link to the person.h, which has the IOStream and STD classes included, we should be able to just write cout here without having to also include them here too, because we've got access through including the person.h file in the header file of Soldier. Okay, so this is helpful. We don't have to keep including IOStream and writing using namespace.std. And so here we should just be able to say firing weapon. Okay, and then end line. All right, so again, similar formats here. Let's now go back to the main CPP. And because this is a child class, we do actually need to include a dedicated reference to that soldier, because the person class doesn't have any links to the child class. So it's the other way around. The child class does have links to the person, but we would need to include the soldier in a dedicated way. We might possibly be able to get away without having the link to the person now, because that's included in the link to soldier. All right, so we could try that. If you really want to cut down the amount of code, you can just include the children rather than the parents, but it's not a major problem. And let's just set up a new title here, exercise 2. And again, I think we just want to create a dynamic instance of soldier and call some of the parent member functions and some of the child member functions just to check that it works. Okay, so I've only currently got the crawl member function working, so I'll call that instead of stand. But of course, once you set up stand, you'll be able to do that. All right, so same format here for soldier. So set up a soldier pointer and then call the soldier constructor, assign through the keyword new. Oh, I misspelled that, sorry. There we go. And let's now call, oh, I misspelled that too. Sorry about that. Let's get that right. And then let's call the, let's try calling crawl first, because that's the important one that we need to make sure we've got access to, which looks good. And let's just then call the fire weapon, which is unique to the soldier. So crawl is inherited. That originates in the person, as we saw there. But because we've inherited publicly, we should then have access to that member function. And we should also be able to call the member function that's unique to the soldier. So let's just give this a go and check that it runs. Let's try recompiling it and rerunning it. And there we go. We've got that printed to screen. So that's good. That gives us confidence that we've set this up to run as it should. Okay, so I hope that gives you a good start with creating classes, implementing inheritance, using header files, CPP files, and also being able to call the member functions. Why don't you now have a go at some of the remaining exercises here, which take it even further and add in extra details and see how you get on with that. Okay, so give it a go and hope you get on okay with it.